We have a good one for you today. Stick around, let's watch.
Something that crosses your mind, but you don't say it out loud because if you did, people would think you're crazy.
I'm gonna put it out there. Hi, my name's Leah. I'm a scientist, and one of the things that I think about
All right, so she is a scientist, but she's a clinical researcher, not a physicist. So that'll be important information for what you're about to see.
quite frequently is the mounting circumstantial evidence to suggest that the world around us and our reality is just a product of a large, elegant computer program. Now, the evidence
All right, so we're about to talk about the simulation hypothesis, so, put on your skeptic hat.
for this is coming from research out of biology, cosmology, computer science, physics. The one I'll talk about today.
So I'm not familiar with any research coming from biology, and any evidence that's coming from computer science is not really evidence in any sense of the world. Remember, computer science isn't a natural science. It's a science about describing algorithms and data structures that we develop. Now, what you might do in computer science is you might see that there's a similarity between data structures and algorithms that we produce, and then things that we see in nature. But again, that's arguing by analogy. As far as what the evidence shows coming from physics and cosmology, that's going to be very, very loose evidence. Remember, what all of this simulation hypothesis stuff is based on is basically string theory, which has no evidence, but we'll see in a minute.
Due to time constraints is coming from the world of theoretical physics and string theory. Now, what you need to
Exactly as I thought, we're going to be talking about string theory here. That should be setting off alarm bells in your head. There's no evidence about that string theory is even true.
know is that the math that describes the physics at the atomic level does not jive with the math that describes the physics at the large body planetary type level. And so string theory attempts to unify these two realms of physics. String theory essentially says that everything that you can see around you at its tiniest level is really just a series of little one-dimensional strings. They can be open, they can be closed, they can resonate at certain frequencies, but they have a discrete conformation. And depending...
Okay, so that was actually a fairly good lay explanation of string theory. String theory is an attempt to unify quantum mechanics and gravity, which is a really, really hard problem, something that I'm working on. It's something that a lot of people are working on. String theory is by far the most popular version of such a thing. And so overall, her explanation is pretty good. I'll just go into a little bit more detail. Basically, the idea of string theory is that you have these tiny little loops of string. They're just loops of something. And the way that they can oscillate, the way that they can vibrate will correspond to different fundamental particles. So if they vibrate one way, you'll get electrons. If they'll vibrate another way, you'll get a quark, rather, not a proton. If they vibrate another way, you might get a photon. Or if they vibrate a special way, you'll get a graviton, the particle that carries gravity.
How they are configured and how they resonate, they may be a car, or they vibrate a certain way, it may be a tree. Now, this is very...
Okay, that's actually all right, but we don't really need to talk about string theory in order to talk about trees and cars. By the way, earlier she said something about a discrete a discrete conformation. I'm not really sure what she meant by that, but presumably she meant a discrete configuration.
Now, I guess it sounds very similar to our computing. Computer programs...
All right, so I don't really see the similarity here. The issue is that in order to get, say, simulation theory from string theory, you have to go through several steps of getting further and further away from reality. So first step, we don't even know if string theory is true. So all of this evidence is based on string theory being true, which we have no experimental evidence that actually supports that idea. So keep that in the back of your head. We don't know if string theory is true, but let's just assume string theory is true. Well, if you do string theory in something called anti-de Sitter space, which is a different kind of universe than the kind of universe we live in something called a de Sitter universe, probably. If you do string theory in this anti-de Sitter universe, then there is a conjecture that there's a relationship between the space-time geometry of the anti-de Sitter universe and some sort of quantum field theory that lives at the boundary of this universe. This is the notion of holography. It's this idea that you have a lower dimensional thing without gravity describing a higher dimensional thing with gravity. Again, this is conjectural. It was first proposed by Juan Maldacena in, I think, 95. And while it's developed a great deal of interesting things, we don't know if it's true. There's probably good evidence that it is true, but there's no proof, there's no experimental data, no observational data that says it is true. Now, the last step to get to actual simulation hypothesis is you have to look at this business about holography. You have to examine how the entropy of states on the quantum field theory relate to the space-time. Now, the trouble is we can describe entropy in a whole bunch of different ways. There's a information type of entropy, which we talk about when we're talking about computers, but there's also like physics-based entropy, where we're talking about how disorderly a thing is. And it turns out if you squint really hard, you can kind of relate the two. But at the end of the day, we're kind of arguing by analogy. We see these relationships between physics-based entropies, and we see, oh, those kind of look like the information science-based entropy. And we say, well, maybe there's some sort of quantum stuff, quantum error-correcting codes or something, living in this holographic world. And Yeah, sure, you can make that analogy, but that's not evidence. And at this point, we're 4 steps removed from reality. There's no actual evidence here saying that we live in this holographic universe that is all just a big simulation, right?
Are built on another discrete system, something called a binary system, ones and zeros. These are called bits, and these are in standard classical computing, or in quantum computing, they're actually superimposed, and that's called qubits. But regardless, they're...
Okay, so we all know how computers work. Roughly, you have bits, and when you arrange those bits in certain configurations, you get computer programs and the like. I don't know why she brought up quantum computing. It's not really relevant here.
In a certain conformation, a certain discrete
configuration
pattern, and they operate in a certain way to make computer programs and a projection. So the next time you want to impress a date or maybe get rid of a date, let them know that you truly think that we may just be a large version of The Sims.
All right, so basically she didn't even make the argument about the entropy or about the quantum error correcting codes, which is usually what shows up when we're talking about these kinds of simulation hypothesis stuff coming from string theory. But the point is there's no evidence, at least as far as string theory cosmology is concerned, that we actually live in a simulation. So I hope you enjoyed. Catch you in the next one.